This is my presentation on circuits and cochlear implants. So to give a little overview, essentially cochlear implants are devices that assist people who are profoundly deaf or have severe hearing loss. They work by sound being picked up by the pin of the ear, allowing sound input to direct through the external processor, which detects sound with the microphone and encodes it into a radio frequency sent via an RF link to an internal receiver, which decodes the signal, sending it to the electrode array, eventually the auditory nerve, and then the brain for perception. However, the external processor is limited with storage capacity, loss of energy through transfer, and aesthetics, leading to new circuit development and devices. So this is the fully implantable cochlear implant. New research and FDA-approved trials are looking at fully implantable cochlear implants to decrease power dissipation and improve sound signaling. And many of these suggest the use of PZT cavaliers that have different resonance frequencies stimulating the auditory neurons according to power level and frequency of input signal. And the study that I looked at also implemented a logarithmic amplifier to help amplify the PZT sensor output and compress the input sound range to the electrical range of the cochlea. An important change here was the use of the logarithmic amplifier at the first stage in this circuit, and the dual function of the amplifier to amplify and logarithmically compress signals eliminates power consumption associated with a compression block in many other circuits. And the main finding of this work is that front-end signaling conditioning circuit here has the lowest power consumption compared to previously done studies. And then my motivation was that I was first introduced to this by my boyfriend's little cousin who was born deaf. From this project, I've really been able to see the ways that improving circuitry can improve the device's power consumption and longevity. And then to go into some of the sociocultural significance here, essentially 360 million people have disabled hearing loss as of 2017, and 1,200 people worldwide use cochlear implants, and it expected that hearing loss will increase in the future. So this is a widely important topic that affects many people. For physics applied to this, my analysis of circuits, I was really looking at Kirchhoff's laws applied to the circuit, breaking down the more complex circuits that I'm looking at in series and parallel, knowing that in series, the current flowing out of any junction must equal the net flow of current out of that junction, and that the sum of all potential differences in a closed loop must be zero relating to voltage. And then I applied Ohm's law as well, which is I is equal to V over R. And then here, important mini circuit of many of the complex circuits. Here, ZT, one component is the total impedance between the intracochlear and ground electrode, and the ground electrode is located in the scalea tympani to optimize communication with auditory nerve fibers. EP is the polarization impedance, which is equal to the polarization resistance RP plus CP polarization capacitance, RP representing the restriction of charge transfer in the electrode-electrolyte interface. P is the polarization capacitance, also related to the electrolyte-electrode interface. Both are important in protecting the electrode when voltage is applied. And I is the constant current flow generated by a external battery. And ZT is equal to ZA plus ZP, which was noted in this study. And ZA is equal to RA being the resistance, which is in series with the parallel capacitor CP and a resistor RP. Physiologically, RA represents the bulk surrounding tissue around the electrode inside the cochlea. I created a model that basically shows where this circuit that I just described would be spatially, along with my own circuit diagram here. That would be located in the cochlea along the electrode array. The ground electrode, though, would be located in the scalea tympani entrance right here, where I have the auditory ossicles ending and leading into the cochlea. And then I basically just represented all of the components spatially to give a better breakdown. And I chose this because Plaidio was a good medium for tissue, different colors to indicate like different regions to symbolize what my mini circuit would look like at that point. And it does a good job of breaking down my component. I'm confident my model is understandable, but I feel like it's somewhat inaccurate just because it's hard to create that electrolyte electrode interface. And then for my analysis and comparison, I compared a fully implantable cochlear implant circuit with a zinc air battery, which is standard in cochlear implants. I compared their total battery power or capacity, and as seen, the zinc air has a higher capacity compared with the fully implantable. The total voltage, though, was greater for the fully implantable cochlear implant, 1.8 to compared to approximately 1.4 volts. And then I analyzed their power consumption. Now the power consumption listed for the fully implantable cochlear implant gave me a standard value for a single stimulation, which wasn't that useful because many look at the total battery life rather than one stimulation, which will happen 100 times in 8 hours though. So then I looked at what the total battery power over the total battery life would create power consumption wise. From that, it is notable that the standard cochlear implant consumes more power power over its lifetime total, which is actually less hours compared to the fully implantable. And then some errors here. I analyzed the fully implantable cochlear implant. Again, only focuses on a single stimulation in its study, but it still provided useful information. Additionally, the fully implantable cochlear implant where it's at now with the 288 hours of battery life would not be sufficient for implantation. I did hit a lot of roadblocks with patents and withheld information from a lot of companies that actually produce these cochlear implants. And even in the fully implantable paper, it did not specify battery parameters. And then looking at the future of these devices, some newer sources propose energy harvesting, where a battery for a fully cochlear implant can generate power from natural vibrations. Typically for these, magnetic induction is common in cochlear implants, involves a non-zero electric field throughout the tissue, which limits the maximum amount of power harvested. So promising for future development of energy push through electronic circuits.